So in this video, we are learning about functions and function notation. Now, function notation is typically something that tends to confuse people the first time they see it. They say, well, what's this new kind of symbol we're dealing with? It seems a lot more confusing, but essentially function notation is everything we've kind of been doing since graphing lines in linear relationships. If you remember when we graphed a line, we said that we would, to figure out how the x and y relate, to figure out our points, we would pick some x values to substitute in. So we'd substitute some things in for x and we'd get something out in y. So you would see these written, maybe instead of this, as y equals this. So y equals this kind of quadratic relationship, or it would be a linear one in other cases. This thing, f of x, communicates the same idea. So we kind of think of this almost as a machine. We think of it as inputs and outputs, okay? Something goes in place of these x's. So the thing in this bracket tells us what we are substituting in for x. That value goes in. Once we evaluate it, we get something out. That was our y when we dealt with linear relationships, for example. We are doing the exact same thing when we think about functions. We're putting something in and we're getting something out. And this notation communicates that to us in a really nice way. So f of 3, that means that 3, we're trying to find what comes out when you substitute 3 in for the x. So what we're going to do for this first one to actually evaluate this, f of 3 is going to equal this expression on the right-hand side, but with 3 substituted in everywhere we see x. So this is going to give us 3 squared plus 5 times 3. Anywhere you see an x, a 3 gets substituted in. Now that gives us 9 plus 15, which gives us 24. Same thing happens for this one. The input is 0. 0 goes in for all of the x's, and we get out our function of x, our f of 0. So what we're going to do, just sub in 0 everywhere. And this guy here is just going to give us 0. 0 squared gives us 0. 5 times 0 gives us 0. 0 plus 0 gives us 0. So last one, we have f of negative 3. So our input is negative 3. So everywhere we see x, we are going to substitute in negative 3. Now you can use brackets or you can use the multiplication symbol. It's up to you which one you would like to use to show this. But this gives us 9 minus 15, which gives us negative 6. So we have found here a whole bunch of outputs for different inputs. We're putting something in and something is coming out. Now we can actually do this for other pronumerals and even expressions, as you see where I have example 1. So what we're going to do, we can sub in other different types of inputs in here. We can substitute really anything and see what comes out. What we're going to do for the first one, we are substituting in a. So our input is a. Anytime we see an x, we are going to put an a. So this thing is going to give us, instead of x, I write a squared plus 5. Now, because this is just another pronumeral, that's my final answer. I can't simplify anymore. For the second one, anytime I see x squared, anytime I see x, I need to put a plus 1 in its place. So instead of x squared, I'm going to get a plus 1 squared plus 5. Now the key word here is simplify. So we can make this simpler by expanding. So what I'm going to do is I'm going to expand this. So I get a squared plus 2a plus 1 plus 5. And that's going to give us a squared plus 2a plus 6. Very last example, our input is a plus h. So anywhere I see x, I'm going to put a plus h in its place. Okay, now I want to expand this and simplify if I can. So I'm going to expand this. So this is a perfect square. So when I have a perfect square that I want to expand, the first term gets squared. When the sign is positive, we add 2 times the product of these two terms, so 2AH and then plus H squared, that last term squared, then plus 5. And this, there's no like terms here, so I can't actually simplify this any further. But this is how we can now start to get to these harder sort of inputs and see how we can get something out. Now, the last one is just a worded question. And the reason I put this in is that many functions have natural restrictions on the variables. So the restrictions are part of the function. A really obvious example of this is when we use, for example, linear models, right? When you model someone's pay and you graph it up. Now, you might remember when we were graphing things up, sometimes we only used this quadrant because there was a restriction on the variables because money was always positive and the time was always positive. So when we actually went and graphed this, we restricted this to just the positive quadrant because time has to be greater than 0, can't be negative, and the money can't be less than 0. Well, it can't be negative, it has to be greater than 0. So if we rub this out, we are going to just read through this question and underline the key terms. Now it's saying a snail is crawling at a steady 10 centimeters per minute, vertically up a wall 3 meters high, starting at the bottom. Now it says to write down the height, y meters, of climbing, adding the restriction on x. So y, its height, now I didn't write this in, but we want to write down the height y as a function of x minutes. So question's not really worded well. We want to write y as a function of x. Okay, so that means x is our input. We get something out in y. Now, this is going to be linear because it's going up at a steady 10 centimeters per minute. So its height is a function of the time that's passed. Its height is going to change depending on how much time has passed. Now, I'm going to get y equals. Now, it goes up after x minutes. It is going to be, its height is going to be 1 over 10 x meters because it's as a function of meters. Of minutes, but our unit is in meters. So it's 1 over 10 multiplied by x because every time a minute passes, it's going up by 1/10 of a meter. So this is a restriction here. This happens where x is between 0 and 30 because 30 minutes will pass before this thing gets to its maximum height, right? 10 goes into 300, 1 over 10 goes into 30 times. So this is our restriction because once we get to 30, it's already climbed to the top of the wall. It's got nowhere else to go. And it starts at 0 because it starts at the bottom. Its height 0 and it works its way up. So this is how we can model a sort of real world scenario using a function. So where one variable, height, is a function of the time, where it depends on the time that passes. That brings us to the end of the video. Thank you so much for watching, and I'll see you next time.